Okay, so first of all, is there any question, any doubt about the exercise for Unit 3 or the exam or any other question? No? Okay, then, well, feel free to interrupt me if you have any question, but then I'm going to solve some of the exercises in an exam that I have uploaded to the virtual campus, okay? The part of the exam that has to do with graphs. So you can see what you can expect from the exam, okay? It will be, well, somehow similar to this, okay? So I'm going to first solve the questions about graphs in this exam, and then I'm going to solve some more exercises from the worksheet for Unit 3. So I'm going to start with exercise 1, which asks us about finding a Hamiltonian circuit in the graph. Okay? So let me copy the graph on my whiteboard. Please take a look at the graph while I copy all the vertices and edges. Okay? And try to think how you could solve this exercise. Almost done here, just the number of the vertices. Okay, so let me switch to the whiteboard now. Okay, so remember that finding Hamiltonian paths in graphs is in general difficult, meaning that if we have a large graph, there is no efficient algorithm that we know of in order to check whether the graph has a Hamiltonian path or not. And of course, we also don't have an efficient algorithm to find the Hamiltonian path in case it exists. So when you are asked a question like this, uh, with what we have studied, the cases in which we know how to find a Hamiltonian path, which in our case is only for tournaments, and this is no tournament. This graph is no tournament. Or it is very easy to show that there is a Hamiltonian path or circuit in this case, or it is very easy to show that there is no such a path, okay, or such a circuit in this case. Okay, so you can start by thinking about what is the case in this situation. Okay, is it possible to find a circuit in this case? And well, if there is a circuit, I'm going to use color green. If there is a circuit, you need to use these edges that I'm using. Okay, these edges have to be in the circuit because they are the only ones that come into 5 and come out of 5. Okay, so in this case, if there is a circuit, you are going to be using these edges for sure. Okay, so you need to complete the edges from these 4 into a circuit in order for this to work. Okay, so what you can do here, for instance, is to complete with this edge and this edge. Okay, and in this case, this is clearly a Hamiltonian path, a Hamiltonian circuit. So for instance, you can go from 1 to 2, then to 5, then to 6, then to 4, then to 3, and then finally again to 1. Okay, so there is a Hamiltonian circuit in this graph, and with this you are done. Okay, so this is one of the cases which I was telling you about last week. If you are given a graph like this one, you just try to find the Hamiltonian circuit. This is very easy in this case because there are very few edges. Okay, so this is the solution for this exercise. Any question about how to solve this exercise? So remember, if you are asked about Hamiltonian paths, you will be given either a tournament or a graph in which is easy to find the circuit or to prove that there is no such a circuit. Okay, imagine for instance that the graph were something like this. Okay, so in this graph clearly there is no Hamiltonian circuit because you cannot use all the vertices once and only once without repeating. Okay, because once that you go to this vertex, you have to decide where to go, either to the left or to the right or down, and if you need to come back, then you will repeat a vertex. Okay, so in this case, for instance, it would be impossible to find a circuit, and it's very easy to prove it. Okay, any question? Okay, so let's move to exercise 2 in this exam. Okay, here we are given an arithmetic expression which is in fixed notation, and we have to first draw the binary tree corresponding to the expression, and then traverse the tree in post order to get the postfix notation. Okay, so let me copy the expression and then I will solve it for you. So 9 divided by 3 times 2 times 4 plus 7 minus 6. Okay, so the weakest operation in this expression is this multiplication here because of the brackets. Okay, so we have a multiplication, and then here in this part, of course, we have a division, 9 and 3, and in this part now the weakest operation is the addition, and then we have a multiplication of 2 and 4, and then the subtraction of 7 and 6. Okay, so this is the binary tree for the arithmetic expression, and then in order to obtain the postfix notation, we have to traverse the tree in post order. Okay, so for the traversal in post order, we need to first go to the left, then here we go to the left, so we obtain 9, then to the right 3, then to the root, which is this division here, then we go to the right here we go to the left, so 2 4 times, then to the right 7 6 minus, and then the root plus and the multiplication here. So this would be the same expression but in postfix notation, because this division is affecting this 9 and 3, this multiplication is affecting this 2 and 4, this subtraction is affecting this 7 and 6, this plus is affecting this expression and this expression, and then the multiplication is affecting this addition and this division. Okay, so it's just a matter of writing the expression as a binary tree and then traversing it in post order. Okay? Any question about this exercise? Is it clear? Okay, so now I can either solve the rest of the exercises in the exam, or I can move to the worksheet and solve some exercises, some more exercises about graphs. What do you prefer? What do you want me to do? The worksheet? Okay. Okay, yeah, I agree because, well, these exercises are similar to some that we have already solved in the lectures, and well, if we have time, maybe we can come back, but maybe it's better to solve some exercises about graphs. Okay, so I'm going then to try to solve, well, first exercise 8, okay? Exercise 8. Exercise 8 is about finding the adjacency matrix for a graph, and then transforming this into an undirected graph and finding the adjacency matrix. Okay, I'm going to do that, and then I'm going to find also not only the adjacency matrix, but the reachability matrix, okay, with the multiplications and all that, because just finding the adjacency matrix is very easy. Okay, so let me copy the graph, and then I find those matrices. Okay. Okay. So the adjacency matrix in the case of the directed graph is like this. From 1 we go to 2 and also to 3, but not to 4. From 2 we can go to 4. From 3 we can go to 2. And from 4 we can go to 3. Okay, so this is the adjacency matrix for the directed graph. Notice that we have 5 ones in the matrix, and that is exactly the number of edges in the graph. So that is a sanity check for us to see that we have done the things correctly. Okay, if the graph were not directed, then we would have a similar matrix, but the matrix would be symmetric. Okay, so we would have from 1 to 2 and 3, from 2 to all the places that have are connected with it, because now we don't consider the direction of the arrows. So from 1 to 2 and to 3 and to 4, from 3 to 1 to 2 and to 4, from 4 to 2 and to 3. Okay, so notice that this is a symmetric matrix, and in fact is the symmetrization of this matrix. If I add ones in all the positions for which the symmetric with respect to the diagonal, the main diagonal is a 1, then I obtain exactly this matrix here. Okay, So this is fairly easy, just computing the adjacency matrix. But now I'm going to compute the reachability matrix, okay? And for that, you know that this is what we call M, the adjacency matrix. This is also M1, the reachability matrix of order 1. And to obtain M2, we need to compute the square of this matrix. Okay, so I'm going to multiply this matrix times itself. Okay, and to do that, remember that we can use the fact that this is a Boolean multiplication, and when we multiply, we obtain sums of rows. Okay, when I multiply this row times this matrix here, I'm going to multiply this one with this row here and this one with this row here. So I'm going to effectively sum these two rows. Okay, so when I compute this Boolean multiplication, I only need to add these two rows here for the first row and so on. Okay, so I obtain 0, 1, 0, 1. Okay, I just add the second and third row. For the second row, I just copy the fourth. Okay, here. For the third row, I need to copy the second. And for the fourth row, I need to copy the third. Okay, so this is M2. This is M2. And we can check that this is correct because for from 1 we can go to 2 with a path of length 2. This path here. Okay, that's why we have a 1 in the second position of the row, and we can also go with this path from 1 to 4. Okay, and so on for all the other elements in the matrix. Okay, so this is M2. I'm going to copy M2 here to have space for the third matrix. So let me erase this, and then I'm going to copy this here. 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0. Okay. And now for M3, I need to multiply either M2 times M1 or M1 times M2 is the same. So, well, since I have this here, oh, I shouldn't have erased it. Okay. So, since I have this here, I will copy it and then times N1. 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. Okay, and I compute the multiplication exactly as in the previous case. So for the first row, I just sum up the second and fourth row, and I obtain 0, 0, 1, 1. Okay, this is correct because from 1 I can go to 3 with a path of length 3. Remember that the 3-order reachability matrix gives us the paths of length 3. Okay, and also from 1 I can go to 4 with this path of length 3. Okay, so this is a 1 here. For the second row, I need to copy the third, which is 0, 1, 0, 0. For the third row, I copy the fourth, which is 0, 0, 1, 0. And for the last one, I copy the second, 0, 0, 0, 1. And this is the third reachability matrix, okay? And now to compute what we call M infinity, the whole reachability matrix of the graph, I need to compute the Boolean addition of M1, M2, M3 together with the identity, okay, which is M0, which is it is the zero order reachability matrix. Each vertex is reachable from itself with a path of length 0. Okay, so it's the identity. Okay, so I know that I will have ones on the main diagonal. Okay, this come from the identity. Okay, and now I check whether I have ones in the positions, in the rest of the positions, in any of the matrices that I have computed. Okay, M3, M2, M1. Because I'm computing the Boolean addition. Okay, so if there is a 1 in at least one of the positions, there will be a 1 in the final matrix. Okay, so here I obtain 1 because, for instance, this is 1, here 1 because of this 1, here 1 because of that 1. Okay, for the second row, notice that all the positions here are zeros. Okay, so I obtain a 0 here. This is because check that you cannot go back to 1 in this graph. Okay, if you start in 2, you can go to 4 and to 3, but you cannot go to 1. There is no path leading from 2 to 1. Okay, so it will be a 0. Here in the third position of this second row, I have, for instance, this one, so I get this one here, and because of this one, I get 1 here. Okay, because as I've mentioned, from 2 to you can go to 4 and to 3. Okay, but not to 1. Also notice that from 3 you cannot go to 1. Okay, I have 0 here, 0 here, and 0 here. But I can go, of course, to 2 because of this one. Okay, I can also go to 4 because of this one here. Okay, and for the last row, I cannot go from 4 to 1. This is 0, this is 0, and this is 0. I can go to 2, for instance, because of this one here, and I can go to 3 because of this one here. Okay, so this would be the reachability matrix of this graph, and the interpretation is that from 1 I can go to any of the other vertices, and from the other vertices I can go to any place among 2, 3, and 4, but I cannot go back to 1. Okay, and this means that 2, 3, and 4 is a connected component, a strong connected component in this graph, and 1 is another strong connected component in the graph. Okay? Any question about this exercise? No? Is it clear? Notice that you have another one which is similar, which is number 4. Okay, number 4. In this case, you are given a graph with 5 vertices, and you are asked to obtain the reachability matrix. Okay, so it's the same, but you need to compute the matrices up to 4, up to M4, and then you compute the Boolean addition of the matrices. Okay? Okay. No questions? Okay, so let's try to do now exercise 7. Okay, exercise 7. So here, let me obtain a new whiteboard. Okay, so here we are asked to either create a graph in the conditions given in the exercise, or to prove that is not possible. Okay, so in all the cases we want graphs with 5 vertices. Okay, and in the first case we have to have an Eulerian cycle, and the edges in the cycle will have to form also a Hamiltonian cycle. Okay, so we need 5 vertices, and we need an Eulerian cycle, which can be seen also as a Hamiltonian cycle. So a Hamiltonian cycle uses all the vertices once and only once. An Eulerian cycle uses all the edges once and only once. What I can do is to just join all the vertices like this, okay? And then the same Hamiltonian cycle is also an Eulerian cycle. If I go from 1 to 2 to 3 to 4 to 5, this is at the same time Eulerian and Hamiltonian. Okay, so this is very easy in this case. Okay, let's see what we are asked to do in the second exercise. Okay, so now we need an Eulerian cycle, and we want the graph also to be two colorable. Okay, two colorable. Okay, so here this is a bit more difficult, okay, because if you try to do something like we did in the previous graph, this graph has an Eulerian cycle, but this is not too colorable, okay? Because if I try to use colors here, for instance, red and green, I can do this for the first vertices, but then here I need a different color, because 5 is adjacent to both 1 and 4, and I cannot use either green or red. Okay, I need to use a third color, for instance blue. Okay, and this is because this graph has a cycle of odd length. Remember that we know that being too colorable is equivalent to not having cycles of odd length. Okay, and in this graph we have a cycle of length. The whole cycle that we have here has 5 edges, so we cannot color this graph with just 2 colors. Okay, so we need to do something different. We also have studied that being too colorable is equivalent to being bipartite. Okay, so it means that we need to have the graph in 2 parts. Okay, so this is something that we can try to do, or we can do something a bit more sneaky, which is notice that in no way in the exercise they are telling us that the graph needs to be connected. Okay, so I can just do something like this, for instance. Okay, this graph has 5 vertices. It has an Eulerian cycle, because this cycle here, 1, 2, 3, 4, uses all the edges in the graph, and it's an Eulerian cycle, okay? But the graph is not connected, okay? So I can do this, or I can try to do, and this is too colorable, of course, too colorable, because I can color these two vertices with blue and these two vertices with red, okay? And then I can use red, for instance, for this one, because it's not connected to any other vertex, okay? Or I can try to go in this direction. This is a bipartite graph. If it is too colorable, it's a bipartite graph. So I can try to do something like this, to divide the graph in two parts, okay? I can divide the graph in two parts, either like that or like this. And remember that in a bipartite graph, I cannot connect vertices which are in the same part, okay? So I can connect, for instance, this vertex to any of these vertices, but not these vertices among themselves, okay? Or here I can connect any of these two vertices to any of these three, but not the two vertices among themselves, between themselves, or the three vertices among themselves, okay? So here I can try to do an Eulerian cycle like this. Well, of course I can, if I don't connect all the vertices, I can do just something like this, okay? I go, well, these are two edges, okay? These are two edges, okay? But if I want, this is Eulerian and it's bipartite, so it's too colorable. I can give color red, for instance, to these vertices here, and then color blue here, okay? But if I want it to be connected, I can go like this, okay? And I have a connected graph with an Eulerian cycle, and it's bipartite, okay? I can do something similar here. I'm not sure. Maybe if I do something like this, okay. No, because if I return here, then this is not a cycle. So maybe I need to go back here, okay? But then this is equivalent to that other one, okay? So let's focus on this way or that way, okay? We were asked only for one way of doing the graph, and any of these two will be too colorable and has an Eulerian cycle, okay? Any question about this this part of the exercise? Okay, so let's see the third part. Okay, now we need an Eulerian cycle, 4 edges, and the graph needs not to be too colorable, okay? So for this, I need to use again this result, okay? So no, not this result, sorry. This result here. The graph is too colorable if and only if it does not have cycles of odd length. So if I have a graph that is not too colorable, it must have a cycle of odd length. And if I have 5 vertices and the graph has 4 edges, the only cycle that I can create which is not of even length is a path of length 3. Okay? With this, the graph is already not colorable. Okay? Because I now need red for this vertex, for instance, blue for this one, and green for this other one. Okay? Whenever I have a cycle of odd length, I need 3 colors at least. I need 3 colors at least. Okay? So now I have 5 vertices, 3 edges, an Eulerian cycle. Yes, because this is an Eulerian cycle. And I need to include a 4th edge. Okay? But the problem now is that this is a vertex of degree 2. This is a vertex of degree 2. This is a vertex of degree 2. And these vertices have degree 0. Okay? And I'm forced to have these three edges like that because of the non-two colorable condition. And when I try to add a new edge, I will increase the degree of 2 of the vertices. Okay, if I add the edge here, then the blue and red vertices increase their degree to 3. If I add here the edge, then these 2 0 vertices go to degree 1. If I do something like this, then I have degrees 3 and 1. Okay, any way that I include the new edge, 2 of the vertices will jump from an even degree to an odd degree. And we know that the condition for an Eulerian cycle is that all the vertices are even. They have even degree. Okay, so if I include the 4th edge, it is impossible to obtain an Eulerian cycle because then there will be 2 vertices with odd degree. Okay, so in this case this is impossible. In cases A and B, I can obtain the vertices as the graph as expected, but not in this case. Okay, any question about this exercise? Okay, so let's see which other exercises we have here in the worksheet. Okay, so the first three exercises are only about drawing graphs. Okay, I think they are not very difficult. Now, if you have any question about them, please tell me. But it's just, for instance, representing here in exercise 3 the different stops of the bus as vertices and then the edges. Well, it's trivial. Okay, 4 is similar to the one that we have solved, to exercise 4. 5 is different. Maybe I will do 5, but let me tell you about the other. 6 is similar. I don't know if we solved 6 or 11, okay, but both are similar. I solved one of them. 7 we have already solved. 8, 9, 10, 11. Okay, 12 is similar to the one that I solved in the exam. 13 is again about traversing these trees. 14 is similar to 10. And 15 and 16 were solved in last week lecture. Okay, so we can either go to 12 or 13, which are similar, or to 5. Which do you prefer? No preference? No? Okay, so I don't know. Maybe I have time to do. Well, I will try to do 5. I'll try to do 5 and then let's see if we have a few minutes to do one of the binary trees traversals. Okay, so here in 5 we have a tree with 5 edges. Okay, um, and it's important to remember that in a tree, let me write it here, in a tree, the number of vertices is equal to the number of edges plus 1. Okay, for instance, if you have a tree like this, okay, notice that we have 5 vertices and 4 edges. Okay, or we sometimes write this like the number of edges is equal to the number of vertices minus 1. Okay, so this is something that it's true for all the trees. We proved that in a previous lecture. Okay, and here we have 50 edges. So we know that E is 50, and then N is 51. Okay, and we remove an edge, and then we obtain 2 disjoint trees. We already know about this. Okay, we also proved this in a previous lecture. But if you have a tree, for instance, like this one here, notice that if I remove, for instance, this edge, then I have 2 trees. I have this tree here and this tree here. Okay, so this is something that happens whenever you eliminate an edge from a tree. You obtain 2 disjoint trees. Okay, and in this case, after removing the edge, the number of vertices in T1 is equal to the number of edges in T2. Okay, so let me write that as what was that? The number of vertices in E1 is equal to the number of edges in T2. So the number of vertices in T1 is equal to the number of edges in T2. Okay? And we are asked to find the number of vertices and edges of each tree, T, T1, and T2. Okay? Well, for T, we already have the answer. The number of edges is 50, and that implies that the number of vertices is 51. Okay? And we have this condition here. We also know that E1 is equal to N1 minus 1. Okay? Because T1 is a tree. And we also know that E2 is equal to N2 minus 1 because T2 is a tree as well. Okay, this is from the properties of all the trees. Any tree verifies this property. Okay, we also know that N1 plus N2 is equal to 51. Okay, and that N1, because I have not removed any vertex. Okay, so the total number of vertices is still 51. And E1 plus E2 is equal to 49 because I have removed one edge. Okay? So if I sum up these two equations, I obtain that E1 plus E2 is equal to N1 plus, okay, I obtain exactly the same information as here. This is not useful. Okay, if you sum up that, you will obtain exactly the same as here. So let me okay, I need to use this one here. Okay, if I use that one here, then it's much easier because I obtain that N1 sorry, E2 no N1 N1 is N1 is equal to N2 minus 1. Okay, And then I can take that here and obtain n2 minus 1 plus n2 is equal to 51. Right? Okay? And that is 2 times n2 is equal to 52. So n2 is 26. This means that E2 is 25. This means that E1 is 24 and that N1 is then equal to E2, which is 25. Okay, so these are the solutions. You just need to write down all the information that you have about the trees and also the properties that any tree satisfies, and then you obtain the result. Okay, so maybe we can do, we have 3 minutes left. We started at 11:05, so if there is no question about this exercise, then I can try to do a quick traversal of one of these trees. For instance, of the first one, let me copy it here. This is T divided by times U double U, no, V, and then plus W power Y and Z. Yes. Okay. So let me do the pre-order, in-order, and post-order traversals of these three. So pre-order, first the root, then the left part, then the right part, starting with the root, then plus, times uv, okay, then plus w power y and z. Okay, then the in order, t plus, and then let me write brackets here, okay, then u times v, then the division here, then w plus y to the power z, and let me close the bracket here. Okay, remember that in order we need brackets, okay, for the expression to be correct. And finally, post order would be T U V multiplication W Y Z power plus division plus. Okay? So the rest is similar. The second tree is similar, and this one is similar, but you need to construct the binary tree, okay, for the expression, and then you do the traversal. Okay, any question? No? Yeah, yes. You mean the final exam? The final exam will be online, probably online, on the date that was scheduled as at the beginning of the academical year, which is, if I'm not mistaken, the 25th of May. Okay. I don't remember the time. Maybe it's 9. But it's the exams calendar. Okay, it's not changed at all. Okay. And you're welcome. I will send an email anyway. Okay, I will send an email after these two lectures to remind you that the date is not changed. Okay. So thank you very much. If there is no other question, no. Okay. So thank you very much for your attention, and please feel free to email me if you have any question. Remember that the exercise for Unit 3 is due on May the 24th. Okay? So if you have any problem with the exercise or any question, email me, or if you have any other thing that you would like to ask, please feel free to email me. Okay? So bye if there is no other question, and we'll meet again on the date of the exam. Bye. Ciao. Bye. Thank you.